Welcome to the Embedded IoT OTA presentation video brought to you by GVSU and DornerWorks.
Hello, I'm Chad Locker, and I'm an electrical engineer.
My name is George Ebling, and I'm a computer engineering major.
My name is Michael Fink, and I'm a computer engineering major.
This is Kendra Hahn, and I'm a computer engineering major.
My name is John Gilman, and I'm an electrical engineering major.
To begin, I'll provide a brief summary of what we mean by IoT OTA updates. IoT stands for Internet of Things, and it refers to embedded devices which have a connection to the Internet. OTA stands for over the air. An over-the-air update means that a firmware image is sent to a device over the air, in this case Wi-Fi, for update. For our project, we used a web application to upload new firmware images to the cloud, and then edge devices, the IoT devices, download that firmware image and reboot to the image that they downloaded to perform the update. The main goal of this project was to create a portable library of functions to perform OTA updates for future IoT projects on various platforms. Now I'll go over some of the major specifications for this project. For the edge devices, one of the major specifications was a connection to Wi-Fi in order to download images over the air. This also included network communication in order to communicate with the web application and receive notifications that updates are available. When the update is downloaded, a checksum must be performed to calculate whether that update matches the image that was sent over the air. Rollback protection is used to boot to the previous working firmware image in the case that a checksum is not passed or an error occurs during the update process. Another major specification for this project was to complete a custom hardware board in order to demonstrate a working over-the-air update. In order to ensure that the functions created for the project were generic, the project was implemented for 2 different boards with different processors and 2 different real-time operating systems, also known as RTOSs, which were FreeRTOS and Zephyr. For the web application, there were fewer specifications, but the most important were that it implement Amazon Web Services for cloud storage and to host the application, and that it be able to initiate updates with the edge devices.
For deploying updates, this begins by selecting a device group and then selecting the update to deploy to those devices. Then notifying the devices that there is an update ready. Notifying devices means sending an MQTT messages to all the edge devices. And when the device hears an MQTT message and sees that it is meant that the update is meant for that device, it will use HTTP to download the update, then perform an image verification check with that checksum, and then once that is finished, it will restart and load the update. In the event that the device fails to load the update, it will perform a rollback to the previous working image.
Next, we'll talk about the project implementation. 2 different development boards were used to develop the firmware for this project. The first was the NXP RT1060 evaluation kit with a Panasonic Wi-Fi module. The second was the microchip SAM E54 evaluation kit with the microchip Wink 1500 Wi-Fi module. Firmware for both boards was developed simultaneously, with the team splitting up to work on the bootloader and the networking components of the firmware. At the end of the project, they came together to combine these different functions and create a full over-the-air update. In addition to this, a web application was developed to be hosted on Amazon Web Services. The main functionality of the web application was not to look pretty, but to allow us to communicate with the boards and initiate an update. This was done by creating a web application that could listen to and send out MQTT messages to the boards, and also interface with the Amazon cloud storage in order to upload images to the cloud and create a URL to send to the boards in order to download those images.
Two messaging protocols were used to complete the over-the-air update, the first being MQTT and the second HTTP. MQTT works by having the centralized MQTT broker that handles message passing. They can determine based on who is subscribed to a topic, who should be receiving messages. In this case, the web host publishes a message to the broker, and the edge devices will then be receiving those updates because they are subscribers to the topic. This also works in the other direction, where an edge device can publish a message, and the broker will send it only to the web host. That edge device in the bottom does not receive the message because it is not subscribed to the topic. With HTTP, the main implementation that we have of this is for GET requests of the edge device. So when there is an update available and the edge device requests the update with the GET request from the web host then responds with the update.
This is a demonstration of the IoT OTA update on the RT1060 eval kit. In the terminal, initialization messages are printed as the board is connecting to Wi-Fi. Now that the board is connected, I will initiate the update via the web application. The MQTT topic that the board is subscribing to is the same topic that the web application will send out a message on. The board has now successfully connected to the topic. The MQTT message contains a URL to the S3 bucket containing the image to be downloaded to the board. The board erases the flash partition where the new image will be stored, then sends a GET request to download the image via HTTP. Each of these TCP data received messages represents a TCP packet containing a portion of the image. As these are downloaded, it is saved to flash. Once the image has been completely downloaded, the TCP connection is closed. At this point, the board can be reset and it will boot to the new image and perform a checksum to make sure that the image was downloaded correctly. If it was not downloaded correctly, then it will roll back to the previous image on the board. Thank you for watching this demonstration.
While working on this project, we faced three major challenges. The first being our limited experience. While working on this project, we had to perform a lot of research and do a lot of trial and error to understand and learn how to work with these new platforms that we had never had experience with before. We had to do a lot of research to learn how to use FreeRTOS and understand where we can go with Zephyr. We had to learn how to write and debug bootloaders. We, for the first time, were writing our own networking wrappers. And many of us, this was the first time of using C and C++ for complex embedded applications. The scope of this project was our next challenge. As we did the research and gained experience, we learned that there were going to be things that were just outside of our capabilities for the complexity of this project. The first of those being we had to drop the second RTOS, and this was Zephyr. We learned that this was going to be, there's too much time had been spent, and there was going to be even more time that needed to be spent in order to get the application to be working with Zephyr for an OTA update. The second specification that we had to drop was the custom hardware. We found that there was going to be too much time required to complete the build of the hardware application, of the custom hardware board. The third challenge we faced was the time constraint. There was a lot of experience and a lot of knowledge that needed to be gained. And once we had gained those, there was a lot of time that needed to be used to actually complete the project to get it to the final working state.